Okay, welcome back. We're working with another turbomachine problem. In this problem, it states that a centrifugal pump running at 3000 RPM pumps water at a rate of 0.6 meters cubed per minute. The water enters axially and leaves the impeller at 5.4 meters per second relative to the blade, which are radial at the exit. If the pump requires 5 kilowatts and is 72% efficient, estimate the basic dimensions, which means the impeller exit diameter and the width, using the Euler turbomachine equation. Okay, so this problem gives us a lot of information. So the first step is actually list out everything we know from just the problem statement. So the first thing I see is the angular velocity of the pump. So it's 3000 rotation per minute, and we want this in terms of radian per second because that's what we'll be using to calculate stuff in the equations. So this is going to be converted into radians per second, and that ends up being 100 pi radians per second. We're also given the volumetric flow rate, and this is in terms of meters cubed per minute, so we have to convert that to SI, which is in terms of seconds, so it'll be something like this. Okay, and the next thing we are given is the water enters axially, and what that means is that water enters radially outward, perfectly radially outward into the impeller. What we can say is that tangential velocity at the inlet, so V1 tangential, is simply 0. Because all of the velocity components lie in the normal direction due to water entering axially, or in other words, entering radially in terms of the control volume. We're also given that the power required for the pump is 5,000 watts, and we want this in SI as well for the equations we're going to use later. And we're also given the efficiency of the pump, which is 72%. Okay, and then it tells us we could use the turbomachine equation, which was derived in previous videos I've made, or examples that I've done. So we could say that the ideal turbomachine equation is rho times AV times these values. Okay, so this is the ideal equation. That's if the pump uses all the power it's given. But since the pump is 72% efficient, what we have to do is multiply this entire value, what we get, by the efficiency. So we could multiply it by that. So now this is the unideal case. You multiply the efficiency by the power input. And we actually could simplify this equation because we're told that water enters axially, which means the tangential component at the inlet is 0. So we could say that this is 0. So this equation simply becomes rho times the volumetric flow rate times V2 tangential times U2. So from that equation, we actually can define the tangential velocity because we're given U2, or not directly given, but we can solve for U2. We're given the volumetric flow rate, we know the density of water, and we know the efficiency and the power input. So we could redefine this in terms of the tangential velocity at the outlet. Okay, so there's actually one more detail that the problem statement gives you that I didn't recognize at first. So it says that the relative velocity is given, which I didn't write down. So the relative velocity at the outlet is 5.4, and that's with respect to the blades. And we are told that the relative velocity is radial at the exit. So what that means, this is the normal component of the absolute velocity. So let's say we drew that velocity triangle. So like this is the outlet of the pump, so this is the blade. So this is like the blade. And let's say it's rotating in this direction at omega. So then this will be the U component, U2. This goes radially outward. Assume this is perpendicular. This should be perpendicular. So this will be W2. Therefore, this would be V2. So what that means is that the tangential component of the velocity vector is the same as U2. So from this picture, we could say that V2t is equal to U2. And that's simply because the relative velocity is perpendicular to U2. So there's no component of the relative velocity in the tangential direction. So we could directly state that the absolute velocity in the tangential direction is equal to U2. So we could further rewrite this equation to say that this equals V2 tangential times the efficiency W dot rho AV times V2 tangential. So we could define V2 tangential in terms of these parameters right here. So we could write this. So this is what we get for the tangential velocity. So if we plug in these numbers, what we get is 18.974 meters per second. And we actually could use this to define the geometry of the impeller exit diameter and width. So knowing that U2 equals V2 tangential, we could also say that equals omega times R2. So we could define the geometry of the diameter of the exit based on this equation, because we could define R2. So R2 is simply V2 tangential divided by omega. And you get 0.0604 meters, or 60.4 centimeters. Now we could use the continuity equation to find the cross-sectional area at the exit. So we know the volumetric flow rate must equal, under steady state conditions, the cross-sectional area at 1 times the velocity of the normal component at 1. Actually, these should be 2 since we're looking at the outlet. So we could rewrite this even further to say that 2 pi R2 B2 times V2 normal will give it the volumetric flow rate. So the only thing we don't know is B2, so we could find that. So B2 equals, okay, so there's only one slight problem that we haven't defined yet, and it's the normal component at the exit. So that comes back to how the problem statement was worded. If we look at the problem statement, it says we are given that the relative velocity at the outlet is radial. So that means this is perpendicular to the linear velocity of the pump. Therefore, the V2 normal is simply W2 because this points radially outward or normally to our control volume at the exit. So we could say that V2 normal is equal to the relative velocity at the exit. And what you get is 0.00488 meters or 4 centimeters. So the diameter of the exit impeller is simply 1.208 meters, and this thing is by the blade width at the exit, which equals 0.0488 meters. So this is the geometry at the exit. Okay, so hopefully this problem was helpful. I think this is a very good problem because it defines a lot of things in terms of vocabulary in the problem statement. So understanding what it means when water enters axially in terms of a centrifugal pump, how to use efficiency, making sure that you're using the right units, and understanding how to look at your velocity triangles so that you can define these velocities to help you get through these equations. So with that being said, I will see you in the next video.